the reliable transport layer. Remember, there are two types of transport layer. There's connectionless and connection-oriented. So here we're talking about the connection-oriented transport layer, which is trying to make the application believe that it's running over a reliable network. So for the transport layer to give the impression of a reliable network, obviously it will have to do retransmissions. Whenever it sends something and it doesn't get an acknowledgement, it will have to retransmit it again. So that's where we are getting those duplicates. So for example, the application issues a connect request to the transport layer. As we said, it is a job of the transport layer to send an SYN across to the other side. So when an application wants to connect, an SYN will be sent. So that will be the SYN sent by the transport layer to the other side. And then we say that once the SYN is sent, another SYN will be sent back. So let me draw here the IP layer. So this is the IP layer. So in order for the transport layer to give the application the idea that everything it sends is received as sent, if an SYN is sent trying to create a connection and a response is not obtained in good time, then the transport layer has to retransmit. If an SYN gets lost, the transport layer has to retransmit it because it doesn't want the application to know that underneath it, there's an unreliable network. So we say that in the process of trying to send those SYNs, trying to retransmit lost SYNs and things like that, or even data, when the application gives it data once the connection is established, and the transport layer sends its data to the other transport layer, then it wants to ensure that that data has arrived. So if the data arrives and there's no acknowledgement, remember we're using the sliding window. So the transport layer is using the sliding window protocol to ensure that everything is reliably sent. So if data is sent, it also must be acknowledged. So therefore, if the transport layer sends data and does not receive an acknowledgement, it will send it again and again. So in the end, we end up having duplicate SYNs and duplicate data segments. But now, remember this, that on the network layer, which is unreliable, the network layer is unreliable. So let's assume that the transport layer has sent an SYN. Let's assume the transport layer has given an SYN to the network layer. The network layer has sent it and then it got lost. So it got lost somewhere. This SYN got lost. With the network layer, it got lost. So now the transport layer has sent another SYN. And maybe that one delayed and the transport layer sent another SYN. So now we have duplicate. The first one got lost, the second one got delayed, and now there's a third one. So there's a delay for the second one. So notice we have duplicate SYNs. The unreliable network layer does not know they are duplicates because an unreliable network does not try to make things reliable. So it even doesn't care if they're duplicates. So the network layer will pass the duplicates, both of them, even if there are 10 duplicates. The network layer does not know they're duplicates because it doesn't keep track of data. So it will pass the duplicates to the transport layer. So it is up to the transport layer to figure out that these are duplicates. So I want you to remember the difference between the network and the transport layer and what they are trying to do. The transport layer is trying to create a reliable environment for the application. The network layer does not care about reliability, so it can lose data. And when it is given another duplicate, it sends it as though it's the first time it's sending that data. So when the duplicates arrive, the network layer will just pass all of them to the transport layer. Just give me 1 minute. Just 1 minute. Okay, so I'm back. And I felt I needed to clarify that so that we don't lose track of where we are. So what we are basically trying to look at is how the connection can be established when the underlying network is unreliable. We say that if the underlying network is reliable, then the transport layer can be sure that when it sends an SYN, it will arrive. So we just need a two-way handshake where you send the SYN from the client to the server, and the server sends back its own SYN. If the network is reliable, that is sufficient. So if this one is going in this direction, and we are using a two-way handshake, then two SYNs are enough to create a connection in a reliable network. But in an unreliable network, this two-way handshake is not sufficient. Why? Because you may send an SYN, the first SYN may be sent by the client. It takes a long time to arrive at the server. The transport layer, having not received a reply, will retransmit the SYN. So now we have two SYNs in the network. The second SYN may arrive at the server before the first SYN. And then a connection is created using that second SYN, and the response is sent back to the client by the server. But then we say that later on, at a much later on, when the connection has been established, data has been transferred, and the connection closed, that SYN, the first SYN that was sent and was delayed, may resurface. It may resurface later. Then it will create some problems. And we went through those problems one by one, where these delayed and obsolete SYNs or delayed and obsolete data segments can create problems for the connection establishment. So I think we looked at that before in the first session we had in the morning. I don't know if anybody has a question on that part. the problems that can arise when you're trying to create a connection. And I think we highlighted all of them, or we went through all of them, these ones. And there were diagrams to also show exactly what problems we were talking about. So up to that point, I believe we are okay, unless somebody has a question. Or am I assuming we are okay? Am I assuming we are okay and we are not? Anybody with an issue? Say something so that I'm aware.
We are okay.
You're okay. All right. I think the problem that maybe I went over it very fast is the solution. Maybe I went over that very fast, and I feel I need to go over it in a way that explains why that is a solution. So there are several solutions to those problems. One is the need to be able to detect duplicates. Remember that we were receiving SYNs and the transport layer was receiving SYNs and not being sure that they're duplicate, like this one. This one was received after the connection had been closed, and the transport layer was not even aware that it was from a previous connection. And so we need to be able to have the transport layer detect when an SYN is a duplicate, so that it doesn't use the duplicate to create a connection which is unrequired. So that's what we are trying to achieve. So that problem has been solved using sequence numbers. So there should be some sequence number within the SYN that makes the transport layer detect that this SYN, I'm not supposed to use it to create a connection. Or even if I created a connection, I shouldn't have created that connection. There should be a way for the transport layer to know that. Now, I explained to you that something was added to the SYN, which is, it gives both its own sequence number and response to the sequence number of the recipient. But anyway, we need to have some sequence number which the transport layer can use to detect that this is not a valid SYN. Now, the second solution, let me just go through these points, these 3 points here. Now, the transport entity ensures that the SYN sent by both sides have both been acknowledged. Remember that in the two-way handshake, the first one sends an SYN and gets an acknowledgement. So for the initiator of the connection, they actually get an acknowledgement. But for the other side, they never get back an acknowledgement to say that what they sent, the acknowledgement they sent, was received. And it is possible that that acknowledgement may have gotten lost. So this idea of both of them receiving an acknowledgement is important, so that if anything gets lost, they can be aware that what they sent got lost. So this requires that the initiator sends an SYN, and the receiver of that first SYN acknowledges and also sends their SYN. Then the initiator sends a response or an acknowledgement back to the recipient. In other words, let me try and draw it here. You send an SYN this way. It was only two-way, you'd have just received an SYN. So for this one, they have gotten the acknowledgement for their SYN, but this one has not received an acknowledgement. So this one is supposed to send back an SYN with an acknowledgement, so that the connection is only created once both of them receive an acknowledgement. Once both of them receive an acknowledgement, then they can establish that the connection has been established. Now, combined with what I've just said about the sequence numbers, it should be sufficient for both of them to actually know whether the connection they are creating is the right one, whether there's something wrong with that connection. So you accompany this three-way handshake with the sequence numbers I had talked about in the first solution, this one, where you have sequence numbers which you can use in this three-way handshake to know whether or not you are using an obsolete SYN or not. Okay, so we've established that we need to have this three-way handshake where each side receives an acknowledgement. So each side is to acknowledge explicitly the other's SYN and sequence number, which means that each of these SYNs will have a sequence number. So let's assume that one has a sequence number X and this one has a sequence number Y. So the idea here is that each side is to acknowledge explicitly the other side's SYN. So side A will send an SYN with sequence number, with the sequence number X, and is to receive an acknowledgement from B that B has received sequence number X. Similarly, when B sends a sequence number Y, they must receive an acknowledgement from A saying that A has received that sequence number Y. That is the idea. So each of them is to explicitly acknowledge the SYN of the other side, and also to include the sequence number. So you acknowledge and you include the sequence number of the other side. And then if you detect that something is wrong, the sequence number that you are receiving is not correct, then instead of sending an acknowledgement, you send a reset. If at any point in this three-way interaction, you detect something is not right, you don't send an acknowledgement, you actually send a reset request and say, look, I think we are not creating the right connection, let us reset. That is the idea. So the three-way handshake only works to the end if everything is okay. If at any time something is wrong, whichever side first detects that something is wrong should send a reset to the other side. And then that means the connection will not be established. This is the idea of both of them acknowledging. The first one sends an SYN, receives an acknowledgement, and then also sends an acknowledgement for the SYN of the recipient. Now, this is to take care of the data. Remember that also data was surfacing at a much later time. Data would be delayed in the network and would resurface at the wrong time, either within the connection or after the connection has been closed. And then that data item was being accepted erroneously as correct, and yet it should not have been accepted. Now, as I mentioned in the morning, is that to solve this problem, the idea is that each connection must start with a number that is far removed from the previous connection, so that the numbers used for sending data are nowhere close to each other. So that even if data for a previous connection resurfaces, it will be in conflict. Somehow it will be totally off. So I mentioned that, for example, if you have two connections starting from zero, let's assume it was starting from zero, and I think I said something like maybe it's going up to 2000. Then the second connection should start with a number far removed from 0 and 2000, anything in between 0 and 2000. So the second connection could start with a number far removed from that. So for example, we could start with a number maybe 15,000. So we start with a number 15,000 to whatever other number. So that if any data from this connection here resurfaces here, it will be known it doesn't exist. I mean, that one there will be no way it can even be accepted, because the numbers here are starting from 15,000 maybe to 30,000. So that's also a way to eliminate the idea of data resurfacing in another connection. Have connections that have no relationship in terms of numbers. If you are starting them one after the other, you need to have very far apart numbers. So therefore, with those three solutions, we are able to overcome those problems. And I think I mentioned that you need to be able to answer those questions. But first of all, let me go through the three-way handshake and how it operates. So this is a summary, and then I will give you the actual three-way handshake. So the summary, this is a summary of how the three-way handshake operates. First of all, the connection that is created in three-way handshake is a full duplex connection. In other words, each side can send through that connection. Now, the client, which is the initiator of the connection, remember I said clients are usually the ones that initiate a connection. A server never initiates a connection. A server just sits there and waits for requests. So it's always usually the client that actually initiates a connection. So the client that is initiating a connection will choose a sequence number. In this case, I said X. It chooses any sequence number because it's a random number, really. It chooses a sequence number and then puts that sequence number in the SYN packet. Remember, an SYN packet becomes an SYN because the SYN bit is set. So it puts the sequence number in the packet and sets the SYN bit. Now, the server, which is the recipient, or the one which is being requested to connect to, also should choose its own sequence number. And as we said, it should respond to the SYN that it has just received and also send its own sequence number. So whatever the server is sending is both an SYN and an acknowledgement. And then we said each side must acknowledge the other's sequence number. How does it acknowledge it? By incrementing it by 1. So if the client said my XYN is X, my X sequence number is X, then in the acknowledgement, the server will say, I acknowledge X plus 1. In other words, I acknowledge that the first data item you're going to send will start with X plus 1. So that X becomes the sequence number of the SYN, and the data that is going to be sent on that connection will start with X plus 1. So the acknowledgement will contain X plus 1. And if the server sends an SYN of Y, then the client will respond with an acknowledgement that has a sequence number Y plus 1, which means I acknowledge receiving your sequence number, and I take it to mean that the first data you send will have a sequence number Y plus 1. That's really what it means. So they must increment the sequence numbers they get and put them in the acknowledgement. Increment it by 1 and put it in the acknowledgement. So this use of sequence numbers and acknowledgements, this three-way handshake, enables them to be able to detect those obsolete segments they were not able to detect. It will definitely rule out creating a connection that you are not supposed to create, and it will rule out any wrong setting up of a connection. Right. So once a connection is established, the acknowledgements typically follow for each of the data segments. So once an acknowledgement, once the connection is established, then each side can begin to send data. Remember, it's a full duplex connection. So any one of the sides can now begin to send data. But of course, usually it's the client that needs to make a request to the server. So usually the client is the first. But once a connection is set up, any side can begin to send because they have already said which sequence number they will use for the first data item. Now, notice that eventually, once they send the data as much as they want, so if you're starting from x plus 1, it will be x plus 1, x plus 3, until you reach a point when you've sent all the data you want. So assume that they have reached that point where they've sent all the data they want. Then they will eventually terminate that connection. And the way to terminate that connection is to send another message which has that bit called fin set, which, as you can say, is just really for finishing or terminating the connection. So eventually the connection will be terminated by an fin message. So in this particular case, the SYN bit will not be set, but the fin bit will be set to mean I want to terminate this connection. That is if you are terminating the connection gracefully under correct circumstances. But if anything happens during data transmission and you feel you want to terminate the connection abruptly, or for some reason you need to terminate that connection, then you use the reset bit. Remember that all these bits are in those 6 bits we talked about. If you go back to that diagram I showed you in the morning, you will see all these bits there. There's the SYN bit, there's the fin bit, there's the reset bit. So if you need to set terminate a connection abruptly for whatever, maybe you've received some wrong data item which you are not expecting and you cannot continue communicating with the other side, you send a message with the reset button or the reset bit set. So that's generally how the three-way handshake operates. But now I'll give you in greater detail how the messages are sent. So initially, remember, a connection is opened by the TS user, in this case, the client. How does the client say it wants to create a connection? I've said this many times. It issues a connect command. So in your program, you will have a connect command. So the program that you'll be running will issue this connect command to the transport layer. Now, initially, because you don't have a connection, the connection will be in the closed state. On the other side, when your program is trying to connect to a server, remember the server will already be in the listen state. So as you start this communication on the client, you have a closed state, a closed connection. On the other side, you have the server in a listen state. It has actually opened a connection, but it is called a passive open. Passive in the sense that it already opened it and now it's in a passive state, just waiting for connections to come in. So it's called a passive open. What the client is doing is called an active open, because it's actually the client that initiates a connection, the initiation of a connection. So whatever the client does, it's called an active open because it initiates a connection. So I'm going to the second point there. Now, the initiator, who is the client, remember they are coming from a closed connection state. So the initiator goes into the SYN sent state. As soon as your program executes the connect command, then it goes into an SYN sent state. because the transport layer is going to send an SYN message to the other side saying, I have a client here who wants to connect to you. So in the SYN send state, it will send an SYN message with the SYN bit set. And then, of course, it will put there a sequence number, which we said is a random number it generates, and says, I will start sending my data using this sequence number, of course, +1. So it sends that SYN message when it is already in the SYN send state. Okay, so we say that means that the next number that will be sent, or the next message that will be sent from the client, will have an X+1 sequence number. Now, remember that when this SYN arrives at the client side, remember that, not the client, the server side. Remember the server side we've said is in the listen state. So it will go from the listen state to the SYN received state. So when it receives the SYN from the client, it will move from the listen state to the SYN received state. So now the server is in the SYN received state. And in that SYN received state, it will send back a packet or a message, actually a segment. It's supposed to be a segment. It will send back a segment, and this segment will have the SYN bit set because it is also going to send its sequence number. But it will also have the acknowledgement bit set. So if you go back to those 6 bits, I believe there's an acknowledgement bit as well. So now we have met the SYN, we have looked at the FIN, we have seen the reset, and now there's an acknowledgement. And let me just go back to that diagram because I believe that those bits are there. So let me just confirm here. So yes, I can see the acknowledgement bit, which is the second bit there. There's the urgent bit, then there's acknowledgement. We shall skip that third one there. Then there's the reset, and then there's the SYN, and then there's the FIN. So if the server is sending both an SYN and an acknowledgement, then the acknowledgement bit will be set and the SYN bit will also be set, to show that it's sending its own sequence number, but also acknowledge the sequence number of the other one. As we said, that three-way handshake requires that both sides acknowledge each other. So here the server has received the SYN from the client. It is now sending its own SYN stroke acknowledgement. And we said SYN is where it sets its number. So in this case, the recipient tells the originator that it will start transmitting at sequence number Y. Actually, it will start transmitting at Y+1. So that Y is actually the sequence number of the SYN. Now the acknowledgement will now contain X incremented by 1. So the acknowledgement will contain the sequence number of the originator plus 1. And it's basically saying, I have received your sequence number, and therefore I'm expecting when I receive the next data from you, it will have sequence number X+1. Now, when this is received by the originator, remember the originator is in which state? They're in the SYN send state. Before they receive this response, they will be in the SYN send state. So they will move from the SYN send state to the established state. Because according to them, the other side has responded, they requested for a connection, they've received a response. So to them, they believe that the connection is set, is already established. But remember, the other side has not received an acknowledgement, so it cannot be in the established state. It does be in another state, which we have said is the SYN received state. So it is still in the SYN received state. It has not yet gone to the established state. Now, when the originator sends back a packet because it will have to acknowledge that SYN. So it will send up a packet with the acknowledgement bit set. And the acknowledgement number will be Y+1, which it believes is the sequence number which it will receive from the server when the server begins to communicate. Now, when this message is received by the recipient, then it will move from the SYN sent state to the established state. And then the originator, which is usually the client, then can begin to transmit data with sequence number X+1. So that is how the three-way handshake operates. Now, so this diagram gives you just a summary of all that. Remember that the initiator was in the closed state. They went into the SYN sent state and they sent the SYN. The receiver was already in the listen state by the time it received this SYN. So it moved from the listen state to the SYN received state. And then it sent the SYN stroke acknowledgement back to the client. When the client received that message, it went to the established state. As I said, for it, it has received its acknowledgement, so it can go into the established state. Then it sends the acknowledgement to the other side. And when the other side receives the acknowledgement, it also now moves from the SYN received state to the established state. And at that time, we can now say that the connection has been established. And both of them agree on certain things. Now, if you look at this diagram, it is the state diagram for the three-way handshake. Remember, we saw the state diagram for the two-way handshake. So this one is slightly different. So if you follow what we have just talked about, if you look at this at the beginning here, remember that it is in the closed state. It is in the closed state. Now, when an SYN is sent by the client, the client goes into the SYN sent state, as we said. And then when the client receives a message from the server, it goes from SYN sent to established. That's on the side. On the server side, it's already in the listen state. It's waiting in the listen state. And when it receives a message from the client, it goes into the SYN received state. And then when it receives an acknowledgement from the client, it goes into the established state. So at this time, they both established a connection to each other. Now, I want to go back to those problems. In fact, I will skip to here. I will skip back to the problems we talked about. Each of those problems. So I want you to tell me, and this now is, I expect you to participate. If you have understood the three-way handshake, fine. If you have not understood it, please ask. Because based on your understanding of three-way handshake, I want you to tell me how the three-way handshake will solve these problems. You should be able to use the three-way handshake to solve these problems. So anybody who has not understood the three-way handshake and how it works. Fine. So let's assume we understand the three-way handshake, because we are saying that the two-way handshake is not able to solve these problems. How will the three-way handshake solve this problem? So let me show it to you diagrammatically. So you tell me, suppose we were using the three-way handshake, would this problem have occurred or not? Would this problem have occurred? So let's have some volunteers. Assume we were using three-way handshake. How would we have resolved this problem and created a connection without problems? Okay, Craig?
Yeah, so the thing is, on the client side, we could have not done a
Yeah.
connection timeout. We could have been waiting for an acknowledgement before we do any timeout. So the client is going to be in scene send state as it sends the scene, then the SYN, then the server. It's supposed to go to SYN received and send the acknowledgement. So we won't use a timeout function. The client will just remain. It is in scene send state and it is waiting for an acknowledgement. So it won't do a timeout. It will just stay in that scene send state for whatever time.
Okay, but I think there's something you're forgetting, Craig. Yeah? We already said we are using an unreliable network. The transport layer is operating above an unreliable network, so you cannot avoid the situation where an SYN takes unnecessarily long. It takes unnecessarily, in other words, the acknowledgement takes unnecessarily long to arrive. So it is possible that the client sent this SYN, it took a very long time to arrive here, but let's assume it arrived maybe much later than expected, and the acknowledgement was sent. So the acknowledgement is coming, but now this client has waited for too long, and it has decided never even reached. So let me just retransmit. So here the retransmission is mandatory. I mean, according to the problem we are talking about. Here the retransmission is inevitable because maybe this took too long, or maybe this one has taken too long. Whatever happened, it's taken long, so that set has expired. So it was forced to send another SYN. So what we are saying, for the two-way handshake, we have already seen the problem it will create. I hope you remember the problem it created. Now, what we are saying is, how will a three-way handshake behave in this environment and create a connection regardless? So Craig, I'm giving you a chance to go over it again. Include the timeout. You are trying to exclude it, but I'm trying to ask you that you need to include the timeout. It's part and parcel of the problem.
Okay, so when including the timeout, I think what solves the problem is the sequence numbers that are included in the SYN messages. So when this
Okay.
the SEK of sequence Y comes back, or when the SYN sequence Z is sent to the server, I can't really articulate, but I know the sequence numbers are the ones which help to determine.
Okay, let me guide you here. So we said that the client will send sequence number X, isn't it? So the client here sends sequence number X. What will the server send in response? According to the three-way handshake, what will the server send in response?
Z+1.
Z plus 1? Don't forget, this is a time diagram. So it is sending at this point when it has received this one. So the diagram starts from there. This, whatever was sent, starts when it has received sequence number X. So what will it send in response?
X+1.
X plus 1. What else will it send?
Send Y.
Exactly. So remember, it's an SYN stroke acknowledgement. So the SYN of the server is Y, but the acknowledgement will be X plus 1. Right. So this client here has timed out because of getting impatient. It has timed out, and the next sequence number is Z, which arrives after this one has been sent. So now this one arrives. What will the server client do? Okay, we have somebody, Odhiambo.
I think in this case, the server would be expecting to get +1 of its SYN. So it would drop Z because Z would be trying to establish a completely new connection.
Okay, so the server will receive an SYN with sequence number is Z. So you're saying the server is the one who will detect the problem?
Yeah, I think in this case, the server will be the one to detect the problem. Or at least my reasoning is once the server sends the SYN and the acknowledgement +1, right now the client is supposed to send back Y +1 to the server, to acknowledge that it's gotten the acknowledgement. But now it's getting something completely different, which is Z. So I think it would realize that Z is like a completely new connection. So it would drop it, or I guess if multiplexing was a thing, it would do something. But in this case, I think it would drop it.
Okay. You think it will drop it because what it was expecting? Okay, so let's first of all talk about what is the server expecting, or rather, what will the client send back, because it's a three-way handshake. What is this client supposed to send back?
I think it was supposed to
Or
send
what
back.
will the client do?
I think after the client receives the SYN plus acknowledgement from the server, it should send back the acknowledgement, in this case, Y +1.
So you think it will send back Y +1?
Yeah.
So you are saying this will be Y +1. Now, given that, now I'm just wondering, I actually don't know the answer to this one, but assume it can either send Y +1 as the acknowledgement. But assuming the client says, look, I already gave up on that sequence number X, and I actually now wanted to create a new connection with Z.
Or if that was the case, then I think the client would send the reset and and Z. Yeah, I think that's what would happen.
Okay, so if it decides, look, I have now given up on the X, I sent an SYN with Z, so I expect you to respond to that, but what I'm getting tells me that you're using another number which I'm currently not using. You're sending me an SYN with Y, which I'm now not aware of, so it will send a reset. But it will send a reset, and it will also send a Y +1. So in this case, it would send a reset and an Y +1. So when the server gets that, then it will know what to do. Assuming it had not discarded the SYN with Z. If it had done that, then obviously we just go back to the beginning, because once the client has reset, it means that connection does not exist. So it will definitely send another SYN. Once it has reset, it is bound to send another SYN. Yeah. Now the sequence, I'm not exactly sure what the sequence will be, but either way, the connection will either be created the correct way or it will not be created at all. So I've tried to give the example where it will not be created at all, because this side will recognize that, look, my sequence number is Z, you are sending me an acknowledgement with sequence number y+1, reset, so that we start afresh. And as I said, once it does that, it will send a new SYN with a new number. So once this side receives a reset, it knows that that has been rejected. That's really what a reset means. It just means I have rejected that connection. So obviously, whatever connection it thought it was creating here, this one, has been rejected. So that connection will no longer be in existence. Because remember, it goes into an SYN received mode before it goes to an SYN established. So at this point, it was supposed to go to SYN established, but because the connection has been rejected, it cannot go to SYN established. I think it will go back to closed. If we go back to that state diagram, I believe there's a way it will go back to the right. So here it's SYN received. Now, if it receives anything other than what it was expected to receive, this diagram doesn't show us what it will do. Assume this diagram assumes everything works correctly, but I believe that there's some data that is left out here, which should show what it should do if it doesn't receive this one, because we are assuming it receives an SYN which is correct, then it goes from here into the established state. But suppose it doesn't receive what it was expecting, there needs to be, I think there's another arrow missing there, or there's something missing to show us that it will not create that connection. It will go into another state, which most likely either it's not even it's not even SY, it's not closed. It will go back here to the list state, or it will go to some other state that the client rejected what came from the server. If it rejected, then the connection will not be established. But I think one of you, I think it is you, was trying to say that assume it accepts. So let me erase this. So you're assuming that it received a sequence number here, and it sent back the sequence number y and i+1. And even though this one had sent an SYN with Z, it recognizes that actually it sent a Z after timeout. So if it responds to the x+1 at this point, ignoring this one, so it will respond and say, look, I want to believe that maybe what happened is that my SYN took so long, I timed out before I could receive the reply. So I'm going to acknowledge, I'm going to accept that connection. So it will send back an acknowledgement, and that acknowledgement will have y+1. And even that will work, because once it comes, remember this thing is already in the SYN received state, waiting for a response. And here it gets a response, and so it will go to the established state. So both of them will establish the connection. So whichever way that sequence executes, either way, either the connection will be established or it will not be established. But we will not have a situation like in this case. Remember, in this case, we said the problem with this one is that once the data, they both believe they have established the connection. This one has established the connection with X and Y, and this one believes it has established the connection with Z and Y. So when the data begins, then now we have conflict, because this one is sending from Z+1, this one is expecting from X+1. So here there's a problem. They think they have established the connection, but with the wrong sequence numbers. But with the three-way handshake, there's no way that can happen. Either we all establish the connection with the correct sequence numbers, or we don't establish the connection at all. I hope that is clear. Or somebody still thinks there's something we've left out? Anyone still having an issue with that one? Okay, we go to the second one.
Excuse me, madam.
Yes.
I think, okay. I understand what you said about this, and so I think my question would be: is it possible for a scenario where the server is the one that decides what you're doing is not correct? Because in this case, or at least how I understood it, once the client sends Z as its sequence number, it's kind of given up on the file, the original one. So that's where the reset comes in. But is it possible for now the server to, once it gets X+1 and it's already sent Z, decides to go back to X+1, and then the server now is going to be the one that says, I'm not expecting sequence number Z, what I'm expecting from you would be Y+1, so it drops Z. So the server,
It drops this one.
Yes, it drops
So,
down. So in this case, the server is the one that decides that maybe not send a reset, but decide that what you're doing is not right.
okay, when you start writing programs, you will realize that actually you can set many connections, even from the same application. There's nothing to prevent your application from having 10 different connections or 2 different connections. So this is possible from the application perspective. Assume I wanted to create a connection to get something from one server, or maybe I want to create 2 different connections even to the same server. Now, wait a minute. Can I create 2 different connections to the same server? That is a bit difficult because a connection is uniquely identified by the IP of the client, and the port number of the client. Assume that's the port for the client, and the IP of the server, and the port of the server. So in other words, at all times, the connections should have unique identifiers. And it's good you asked that question. Now, the server identifies all the connections made to it by 4 numbers: the IP of the requester, and the port number of the requester, and the IP of the server, and the port number. So all the connections that are here, each have a unique ID with 4 identifiers like this. So let's assume the IP of the client is, let's just give it a simple number like S. And let's give the port number something like maybe a value of 2. Let's just give the IP of the server a number like T. And the port number of the server, in assuming it's a web server, we give it a number of 80. Is it possible for the server to establish 2 connections from the same client, which will have the value, S2 and T and 80? It should not be able to do that because it will not know the difference between them. So most likely, one connection will be terminated. So I think the one with Z will be terminated. I don't know if I'm answering your question.
Yeah, I think I'm understanding.
Excuse me, madam.
So the second connection will be terminated. When it arrives, the server will just know that, look, I will not be able to distinguish between these 2 connections because they will have exactly the same ID, so I have to terminate one. So the Z will already be terminated. I don't know if I've answered your question, by the way. I don't know if I understood your question, but it was a good question because it has reminded me of something we haven't done yet. We are yet to do that. But I have a question from somebody.
Yeah, not a question actually, madam. On the point of
Yes.
if a server can accept 2 connections, when we were taught about multiplexing, there's I guess something
What do you
about
mean by
threading.
multiplex?
About threading, you can actually connect a server to multiple on multiple instances using threadings or threads instead of the
Say
whole
that again, you
process.
can connect?
You
Okay.
can connect
You said you can
a
connect
server,
what?
a server can have multiple connections, I mean, but if you use multiplexing, yes, on the same port.
How do you use multiplexing?
There
How
are
do you use
for
multiplexing?
each, okay, let's put it this way. You break down the
Let me
chunk
try and
into
draw what
threads.
you're saying. So let me
For
just look for a page where there's nothing so that I draw what you're trying to say. I don't want to eliminate that thing. I want it to remain there. So let me draw what you're trying to. So here we have a server. Yeah, a
yes,
server has multiple connections. There's connection 1, there's connection 2, there's
yes.
connection 3. Yeah, so what are you saying?
On the connection part, each client is connected to a port. So on the port part, instead of
wait a minute,
yes,
let me just follow your argument. So these are clients that are connecting, right? To the
yes,
server.
yes,
So on this side, you're saying there's a client, and by client, I mean a process, a running program.
yes, in its
Okay?
entirety.
Sure.
Because a program can
So those are 3
have
programs running.
yes, and for each program you can divide it into threads instead of actually transmitting it as a whole. You can actually you can use threads, or each process can be what? Actually, I'm struggling to remember the multiplexing issue, but it was something that was possible when I looked it up using multiplexing and the threading.
Okay, let's do this because our multiplexing is coming after the termination of connection. I
Yes.
think the next thing we are going to talk about is multiplexing and also flow control. Rather than think ahead, why don't we discuss that when we reach to that multiplexing part? Because I think at a later time, we are going to discuss this issue. We are going to discuss this issue about how many connections can we even create to a client? What is the possible? Is there even a limit? And also the question, which is what is arising now, how does the server know which connection is which? Because remember the server, they're connecting to the server, and the server needs to respond to all of them. So that whatever this one is requesting, the server will respond back to it. And whatever this one is requesting, the server is responding back to it. And remember, it's being done in concurrently. And that's why it's important for the server to know who is connecting to me. Which connection am I currently responding to? And that's why I was saying that usually the server needs to have a unique way of identifying each connection. And now when we translate this to the internet, for example, how many connections do you think go to a given server? If you take even YouTube, we take any one of these servers that we connect to so often, that most people that are very popular, how many connections do you think they take? Could be millions, could be hundreds. And the server has to know which connection is which. So and so asked me for this video, so and so asked me for this page, so and so asked me for. How does it know without getting confused about who am I responding to? What exactly did they ask me for? So the server must have a very good understanding of which connection is which, so that there's no confusion between one connection and another connection. And that's why I was saying that usually the way it tells apart the connections is by keeping 4 unique identifiers for each connection, where the connection is referred to by the IP address of the client and its port number, plus the IP of the server and the port number that they are using. so that it's very difficult for the server to distinguish several connections that come out of here. I'm not sure how it will distinguish them, but what you're saying is that I can have several connections coming out of there. Really what you're telling me, that it's possible for the server to have, assume there are threads in here. There are several threads that are communicating within this one program, that somehow each of these threads can create a connection to the server, and the server is able to distinguish if these programs are using the same port number. Assume the port number is for the application. Remember, the application is given a port number when it starts running. It's given one port number. Now, that one port number is the one that it will use. Now, if you use just that one port number, then the server cannot distinguish, because these connections, they all have the same ID. So there has to be something else that makes it possible for the server to distinguish, most likely because these threads will have different port numbers from the original program. But they cannot use the same port number and the server be able to know which thread is even talking to it. It's not possible. So what we'll have to find out when we go deeper, and remind me of this issue, how can we have threads here connecting to a given server and the server be able to distinguish them if they're coming from the same application, and if they're using just this one port number that is here? We'll have to find out that. We'll have to find the answer to that question, but that question cannot be answered in what we are talking about now, because right now we're talking about connection establishment. So please remind me of this problem, and hopefully we'll find an answer for it, because I believe there's an answer for it. But for me to answer that question, I may have to talk about so many things I was not ready to talk about now. Am I clear?
Yes.
Yeah, so keep that in mind, and let's talk about it when we are discussing issues to do with how does the server remember all those connections made to it. So we are in the second problem. So I believe we have answered that problem. So let's go to this one. And I hope you know the problem here and how would the three-way handshake deal with it. We said the two-way handshake cannot deal with it. How would the three-way handshake handle it here? Let me have some ideas. Here we have an SYN resurfacing. It's supposed to create connection in this time period, but somehow it got delayed and the connection was created and even terminated. That's when it's resurfacing. Now, can this server here recognize that problem? Or can the client recognize the problem? In the three-way exchange that they will do, one of them has to recognize that this thing has a problem. So can you just explain to me how the three-way handshake will tell apart this problem, or will resolve it? Who wants to volunteer? Okay, so we have Roman Juguna. Go ahead. Okay. Remember, the connection has not been created here. The connection was closed. This connection has been closed. So we are now trying to create a new connection. Notice that the client on this side is creating the connection at this point. But before it actually starts creating this new connection, this one resurfaces. So the connection has not yet been created. It is this K that will be a number far removed from this one. If we are using the three-way handshake, then this K should be far removed from what was being used here. So if this one was going, for example, from 0 to 1,000, this K could be 10,000 or 20,000 or whatever, depending on how many bits are used for the sequence number. We'll have to find out how many bits. I think it's 16 bits. If we go back to this diagram here, I think it is 16 bits. So you need to tell me how many numbers. Where did we have the, yeah. The sequence number is 32 bits. So 2 to the power 2, how many numbers can you accommodate? That should give you an idea of range of numbers you can use. And remember, there's the wrap around. You can always wrap around, yeah? Yeah. So what I'm trying to say, Roman, is this, that it is the client who is going to create a connection with the number far removed from the previous one. But notice that this thing here arrives before this client has actually sent even the connection request. So this one is coming. Okay, I see your point. Maybe it really makes sense. That the I that will come, no, but I'm not sure. Okay, it's possible, but I'm not sure how that detection is done. But I think the generation is done at the point you're choosing this number. So the other side does not know. It just receives the number that was created on the assumption that whatever was creating the number on the side chose a number far removed from the previous connection, which tells me that maybe the operating system keeps some information about what was the initial sequence number that was used and what has been used subsequently, so that the other side may not know that. Remember that this side will also generate its own sequence number, which should be far removed from the sequence number that was used the other time. So I tend to think that that will not work here. So let's just assume that, of course, you can still convince me otherwise, but I think what will happen, this one will be received, even though it is obsolete, and it will be used to create a connection without knowing that it comes from the previous connection. So let's assume that happens, but still I'm waiting to be convinced as to how the other side will know that this sequence number is far removed from the other one. That's the part I'm not sure will happen. But Roman, you can continue. Let's assume that the sequence number arrives and the other side assumes it's a correct sequence number. It is far removed from what was previously used, and then decides to start a connection. So that means it will respond here. It will assume it's a connection request and it will respond. So pick it up from there, Roman, if you can. Mm-hmm. Okay, so tell me, what will the server respond with? Assume the server assumes that this is correct and responds. What will be in the server's response here at this point? What will be? Mm-hmm. 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 Exactly. So it will have I plus 1. Now, when I plus 1 arrives on this side, remember it's arriving at this time. after this side has already sent the correct SYN. This is now when it is creating a connection. So according to it, it's creating a connection with the sequence number K. So now it receives an acknowledgement which says, my sequence number is J, but I'm acknowledging your request for connection and expect to receive data from you starting from I+1. What will the client do? Exactly. Because it didn't send I. It will notice that this side is responding with a number I never requested for a connection starting from I. So obviously it will reset. Notice that the two-way handshake would not have recognized that, so it would have just begun to send data starting from K+1, assuming the connection was created. But in the three-way handshake, it will notice something is off here. It's not correct. I didn't send a sequence number I, and this connection, I cannot accept it. So it will reject it, and the connection will not be created. But in the two-way handshake, the connection was actually created, and we entered the data transfer phase here. So this is data transfer phase, starting from here, assuming the connection was created. But three-way handshake will say no. And so there will be no data transfer phase. There will be no connection created. Good. So we go to the next problem. So here we have a problem. Although this is really data transfer, but let's think through it and see whether the three-way handshake would have solved this problem. Assuming we're using the three-way handshake, could this problem have occurred? Let's have a volunteer. I saw some people who had requested to do the other one. Gregory? So, would the three-way handshake have solved this problem? And how?
I left my hand up for the other one, but let me see and see if I can try and answer that.
Okay, fine. So here we have data. Data is resurfacing after there's a wraparound. Data is resurfacing after we have a wraparound. Do you think this problem can occur?
Maybe I should try.
Okay.
I think the three handshake protocol may solve this by, since it uses sequence numbers that are far-fetched from the last sequences.
Mm-hmm.
That may solve that this particular problem, since when by the time like it's wrapping around and it's coming back to that particular sequence, it will be far after so many other connections have taken place, and they may not be that kind of collision of the sequence numbers.
Okay, somebody give me what is 2 to the power 32. Remember, we looked at the sequence number and we saw the sequence number is 32 bits. So how many numbers can we use to...
4.2 billion.
It's 4,294,967,296.
Okay, so let me just take the 4 billion. You realize that that is a huge space. That is a huge space of numbers. So let's assume that this one, for example, Assume the previous connection. Actually, this one is not even about connection. This is about, it's within the same connection. Eh? So this is within the same connection, which started at, it started at 1. It started at 1. And it continued to 201 to 401. Of course, here we used a shorter number. We used a shorter number of bits. Maybe we assumed something like how many bits would give you up to 1,400? That would be 2 to the power what would give you something like that. 2 to the power 10 gives you what? 1048. So imagine that 2 to the power 10 would give you about 1,048. So this one has used a very small number of bits, something like 2 to the power 10 or 2 to the power 8, something like that. So it's wrapping around after about 401, or if we look carefully, it's about 1401 here. It begins to wrap around after 1000. So it's something we can say maybe 2 to the power 12 or 2 to the power something. Okay, it's wrapping around after 2 to the power something here, 2 to the power 10 or 12 there. Now, in this particular example, we have SN number 1 was sent very early. And then the sequence numbers continued and wrapped around. So let's assume it uses this 1401. So it wrapped around after 1401. I suspect there's a problem with this numbering. So after 1401, it wrapped around to start again at SN1. Then it continued, and then again when it reached around 1401 there, it wrapped around a second time and started afresh. So this thing is within the same connection. There's been no new connection set. It was set, it's just the same connection, but the connection has so much data that it's wrapping around quickly. Now translate that to a situation where you have 4 billion numbers. So you wrap around after 4 billion values. How do you think this would behave? Would this be able to occur? That a number which was sent very early arrives after the value has wrapped around even twice or even once. What do you think? So remember, if you have 32 bits, you start from 0, go to 1, to 2, to 3, you go all the way to 4 billion. And once you've reached 4 billion and you've reached the maximum, I think somebody read out for us what the maximum is, but it's past 4 billion. Then you wrap around and you go back to 1. You start afresh from 0, 1, 2, 3, 4, all the way to 4 billion. And then you wrap around again. And we are saying that this data is still somewhere in the network. What would you say? Would you think the three-way handshake has solved it, or all the solutions we provided would solve this problem? And how? Okay, let's have somebody has an answer. Roman. If the server sends what? Mm-hmm. Okay, just remember that this thing is a sliding window protocol. First of all, let me remind you, we are only showing the data, but let us assume that the SYN was sent here, because we are not shown where the SYN was sent, but the SYN was sent, and the SYN was sent, and the third SYN was sent. Assume it was three-way handshake. So now this is the data transfer phase. We are assuming here the connection has been created. So this is data transfer phase. We have not been shown in this diagram where the connection was created, but we assume the connection was created and it was successful. Then we entered the data transfer phase and we started transferring the first data item, which is SN equal 1. Okay, so that is the assumption here. The connection is established. We are now sending data. And as we send data, we send 4 billion data items before we wrap around. And in this particular case, if you use the example, it means we send 4 billion times 2 data items before this thing resurfaces here. After 4 billion times 2 data items, how would three-way handshake have solved it? Maybe not even three-way handshake. Maybe you need to know a little bit more, but we've already covered those things in your previous courses. There's something here that I don't think would have happened with the, remember, three-way handshake includes this idea of having 32 bits. You know why that's why they have 32 bits? So that it is possible to choose a number far removed from the other one. If you have a 4 billion number space, it's possible to choose what we say. It's something that is far removed from the previous one. So that's part of the three-way handshake. So don't just think the three-way handshake is the 3 data items sent. It includes the sequence number having 32 bits, which means a large space of numbers which you can choose from. Okay, unless somebody has an answer, let me try to answer it the way I would think that that would be the answer for this question. Now, first of all, remember that on the internet, I believe there is, in the internet header, there is some data item that is put there, which every router, what do you say? Every router will do what? Every router will decrement that number. I don't remember what the number is called, but if you look in the header, there is a certain number there that is put at the time when the data is being sent. And at every router, that number should be decremented. And when that number reaches 0, that data item has to just be removed from the network. Please go check your IP header. I think it is somewhere in your notes, just check it. But there's this number that is put there so that whenever, as it goes from router to router, that number is decremented. And that number usually has taken into account the number of possible routers that your packet can go through, if it's coming from one end of the internet to the other end of the internet. So it takes into account. So let's assume there are 1,000 routers that your packet can go through. That number would probably be 1,000 or 2,000 or 4,000 or more than that, depending on how many routers it can possibly go through from one end to the other. So that as it goes through the routers, of course, as we said, it might be slow. At every intermediate node, it will wait until it goes to the front of the queue and make its way slowly through the network. Every router will decrement that number. So I think what you have to think about, if you have all these busy routers on the way, and you have a number like 1,000 routers which you can possibly go through, is it possible for the client to send 4 billion data items and wrap around and send another 4 billion data items before this packet makes its way through 1,000 routers? Because at one point, this number will be decremented to 0. And when it reaches 0, at whichever router it reaches 0, that packet will be dropped. And my answer to that question is that to send 1 billion data items times 2, I think that time would be much longer than the time it would take for a packet to make its way through 1,000 routers and arrive when you have wrapped around the second time. I feel that in this time, this packet would either have arrived, or it would have arrived, or it would have been dropped somewhere. That's just my thinking. It would have been dropped. In that span of time it takes to send 4 billion data items times 2. I just think that it's enough time for this thing to have made its way from one end of the internet to the other end. It would either have arrived or it would have been dropped. So that this possibility here I'm not sure whether it will work. But if it arrives, let us assume if it arrives, can the three-way handshake be able to remove this one? I don't think the data transfer phase of the three-way handshake would do this. Because when it arrives, it will just be taken as another of the data packets. So it will be received, and when the correct one arrives with the sequence number, it would be seen as a duplicate, and it will be dropped. Because remember, in the packet, you don't include the connection number. So you never know which connection that data item was for. It just includes the sequence number of the data. It never includes which connection was it on. So there's no way for the receiver to know that this thing was sent earlier or it was in a different connection. It wouldn't know, because it just looks into the packet, sees a sequence number, compares with the sequence number it was expecting. If it fits within the range of numbers it's expecting, it accepts it. So the only thing that would make this not happen is that large sequence number space, which we talked about. That one would, I think, would be the solution to this problem, as we said. So within the same connection, remember this is within the same connection, that within the same connection, the client wraps around twice and the first data item has not arrived. And it's wrapping around after 4 billion different data items. I don't know whether that's possible. That's just my thinking. I don't know if somebody else has another, what you think? What you think could have happened? What you think may have happened differently? Okay, I give you time to think about that. But now let's think about this one where it arrives in a new connection. And we use that idea of the sequence number is far removed from the original. And here there's no wraparound. Here we don't have the idea of a wraparound. So who would want to take that one? Do you think that this problem would have occurred if you were using the three-way handshake? Someone? Okay, I think there's somebody hand is up. Taylor?
I don't think it would occur because of the concept of taking a sequence number that's far off from what you've recently taken. So This is originally it was 1, ended at 201. And then it went through 201 again. So in this scenario, if it was a 3-way handshake, I think it would have taken something like, I don't know, 1,000. So if it would receive this 401, it would automatically know that this isn't supposed to be here.
Say that again. It will do what?
Once it would receive the sequence number 401, and in this case, it took something far off like 1,000, it would know that 401 is obsolete, so it would discard it.
Yeah. So assume, I agree with you, Taylor. Assume that this one had chosen a number far off from this 1 to 400. So you are choosing 1,000, but let me choose a number like 5,000, for example. Let me just choose a number like 5,000. Okay. So assume that this thing was still in the network somewhere, making its way to its destination. Now, and this one created a connection starting from 5,000. So it makes its way all the way, and it finds its way to the destination machine. So if this one was starting at 5,000, if we take these 400 data items, it would perhaps be at, in fact, they are bytes, they are not even data items. It would be at around 5,401 by the time this one arrives. If a number was chosen far removed from the other one, by the time it arrives, this one would be at 5,401. And because it knows it started at 5,000 and now it's at 5,001, it will definitely know this thing could not possibly be part of this connection. It could not possibly be part of this connection. Definitely not. But remember that this number will wrap around. This 5,400 will go all the way to that 4 billion we're talking about, and then it will wrap around to 0. Actually, I don't know whether it wraps around to the start, which is 5,000, wraps around to 0, but I think it will wrap around to 0. So it starts from 5,000, it will go all the way to 4 billion, then it will wrap around to 0 and start afresh. But the idea here is that if this thing was from another connection, by the time this thing makes its way all the way to 4 billion, either that data item has been dropped based on that number I told you is in the header of an IP packet, or it will have arrived. But it will arrive even before this thing begins to wrap around. And it will be known that because we started at 5,000, we are now maybe at 3 billion and something. This thing was not part of this connection. It could not have been part of this connection. So it will be dropped. But please don't forget that the wraparound takes place. So at some point it will go back to 0 and start afresh. But the time it takes to do that, I think it's enough time for that thing that was lost within the network to have made its way to destination or to have been dropped somewhere. Okay, there's a question, Jerry?
Yes, my question is, in addition to that aspect of having the scene sequences far removed, can you also say that the server can notice that the scene sequence that the client has sent, it hasn't sent the correct, like, an acknowledgement, the acknowledgement that it's expecting from the server? For example, if the server had previously, in now the correct connection, it had sent an acknowledgement of Y. So the client should send in its segment its own scene sequence and the expected acknowledgement sequence, which is Y plus 1. But then this obsolete segment comes in with only a scene of 401. So in this case, can the server notice that this one hasn't sent the correct acknowledgement sequence and maybe perhaps send a reset or something?
Okay, from this diagram is like the first one, where it is assumed, you see, these diagrams were drawn for the two-way handshake. They were drawn for the two-way handshake. And so this was just trying to describe the data transfer phase. So here is the handshake for the creation of the creation of the connection. So if it was using three-way handshake, this would have gone three ways. Before the connection is created, that would have had to happen. Otherwise, the connection would not have been created. So in a three-way handshake, this would have been three-way. So remember, we are turning a problem which was there in two-way handshake into a three-way handshake problem. So here we've just assumed that the three-way handshake took place. And in the three-way handshake, they each said where their starting number would be. So we assume that this one said it will start at 1, and so it went on and sent the 401. Now, if this second connection was being created, what we are saying, it would have involved starting from a number far removed, but it would have been a three-way handshake because we are using the three-way handshake protocol. And so this would have been a three-way handshake, and it would have started from a number far removed from this one. That's why I was giving 5,000 as a possible example. So it could have started maybe at 5,000, and in the three-way handshake, they would have done they would have done the negotiation. Okay, so this side would have said, last time I started from 1, this time I'll start from 1,000 or 5,000 or something like that. Then the sequence number would have started maybe at 5,000 and not 1. Remember, it used 1 the last time, so it could not have started possibly at 1 again. So it could have started at 5,000. That's what I was saying. And then the time it would have taken to send this 401 would have meant that this sequence number would have been 5,401. So that by the time this one arrives, it possibly will be detected as possibly not being part of this connection. So I think you're looking at the connection sequence and you're assuming it's using two-way. It's using three-way. If you're using three-way, the connection establishment will also be three-way. So there's nothing that has gone wrong there. It would have done a three-way, and then we'd have started with data transfer. If the connection was not three-way, we would not have entered data transfer phase. I don't know if I've answered you, Jerry.
Okay, my question was,
Yeah.
in addition to the fact that the sequence numbers are far removed as like a way of detecting, can we also say that the server can check, it was supposed to send like a scene, it's expecting like the next segment should have a scene of x plus 1 and its own acknowledgement. That's what the server is supposed to send back, right?
Yes.
And then perhaps now it receives from the client, the client's scene, and then it notices that obviously the sequence is wrong for the client. And then it also sees that the client has the wrong acknowledgement sequence that it is expecting from the server. Or does that count as a way of detecting also?
Unless you're talking about a different scenario. But if you're talking about this scenario that we are talking about here, I actually don't see how that arises. Because remember that in this diagram, the sending of data is taking place. And I have forgotten here to mention something, and maybe it will become clearer with time. When you see the sequence number 1, this is the number for the first byte. In the TCP transfer phase, you number each of the bytes that you send. You number each byte. So that means that in this transfer, we sent bytes from 1 to 200. Now, this other one we sent from 201, maybe each one of them carried 400. So this one would be at 601. So I think this was more noticeable here, that this is the sequence number for the first byte. So if this is 801, it means that this data segment carried 200 bytes, starting from 601. This data item carried 200 bytes, starting from 801 to 1000. This one also carried 200 bytes, starting from 1001 to 1200, and so on. So these numbers, ultimately, they are sequence numbers, but they represent specific bytes in the data that is being sent, in the packet that is being sent. Okay, having said that, coming back to your question, the way I want to answer it, and maybe I still don't know if I've understood it, but the way I want to answer it, by the time this one happens, this has already taken place. So if this side said, I will start from 1, and it has already sent 1, and this one was accepted, it means that there is no confusion. If this had started at the wrong place, this would have been rejected. But because it is in line with the sequence numbers they exchange during the SYN stage, it means that it is correct. So this one was accepted, and this one was accepted, and maybe the next one was accepted, and so on. So coming back to the question you're asking, that maybe the client sent the data with the wrong sequence number, and this comes after a number of packets have been received. I'm finding that a bit hard to understand how that could happen. I don't know, unless you are talking about the first data item. The first data item is the one that is most likely wrong, because after the sequence numbers have been exchanged, we expect the client to start at the right position. If the client starts at the wrong position, obviously this one will be rejected. But of course, also it is possible, because we have a receive window, we always have a receive window showing us what we are expecting. If any data arrives which was not expected and is not recognized within the receive window, that number will be rejected. So always remember, there's a receive window which tells us what are we expecting to receive. If anything arrives which is not within that receive window, it will be rejected. So what you're asking, maybe I still don't understand it. Maybe you can write it to me or explain it to me better, but I think that will be taken care of by the receive windows. So that if this one arrived and it was not part of the receive window of the server would have rejected it. But the assumption here is that when this thing is arriving, it is within the receive window. Based on its number, it is within the receive window. So there is no way that the server will reject it, because it is expecting it.
Perhaps maybe I should ask another question. After the three-way handshake has been made,
Yeah.
for each data segment that is sent, does the server send an acknowledgement for it?
Yes. They are not shown here, but there are acknowledgements for each data item. And I think I mentioned it when we were talking about the three-way handshake. I believe I mentioned it. There should be an acknowledgement here. It says once a connection is established, acknowledgements are typically follow each data segment. So there are acknowledgements here. It is not shown because it's just maybe to make the problem a little bit more understandable. It is not shown, but there are acknowledgements. Does that make the problem more complicated or less complicated?
Less, or maybe I can write it to you.
You can write it, eh?
Yes.
Yeah, so please send me an email. You write it, I'll think about it. But just notice that these things will be acknowledged. So this one will be acknowledged, and the acknowledge will say, I have received from 1 to 200. I'm now expecting 201. So the acknowledgement will have 201. So when this one is sent, it's from 201 to 400. So the acknowledgement here will say, I have received up to 400. I'm expecting 401. So if you remember what we did in the other, what are they called? Data link protocols, that's what will happen. So each one of them will be acknowledged. So let me receive that question again, maybe through email, and I will think through it, and please explain it in depth so that I'm able to understand it.
Okay.
Okay, so I've taken time on this connection establishment phase, but I believe that with what I have said, you should really be able to understand this three-way handshake. I think we've gone all the way there. We've looked at that one. This is what I was trying to do, but I was trying to do it practically. So we've gone through how the three-way handshake solves all those problems. You can also look at this one and try to see if the three-way handshake solves the problems. Even this one tries to show how the three-way handshake solves the problems. These ones you are seeing here are those obsolete data items that appear from nowhere. That's what this diagram is showing. So look at it and see whether if these things appear from nowhere, they come in and they were not really sent by the host, then how does the three-way handshake solve them and bring order back to the system? So I believe we have really finished the connection establishment phase, and you should be able to answer each of these questions. Each of these questions you should be able to answer. So ideally, we have finished the connection establishment phase, other than the problem from that Jerry is going to send, which we will try to answer next time. Otherwise, we will go into the connection termination phase. Secondly, I want to bring your attention to a document that is in your notes. Maybe you have not seen it, but I want to bring it to your attention so that you look at it. And I told you about it in the morning. Now, I said that in the past, I've asked this question. Having gone through the connection establishment, I've set questions based on this. So let me just read for you this question. It says, a two-way handshake protocol is suitable for establishing a client-server connection in the context of a reliable network service. Describe the normal operation of a two-way handshake protocol. So that just expects you to describe how the two-way handshake protocol behaves in the normal case, which is that you send the SYN and you receive another SYN. Now, of course, you don't say it in those two words that I've said, but I believe you know what I mean. The second question then says, with the help of appropriate diagrams, explain the limitation of the two-way handshake protocol when handling the following scenarios which can occur when we have an unreliable network, which is what we've been trying to say. If you have duplicate SYNs arriving after the connection has been established and closed, how would the two-way handshake be able to do it? Of course, we are talking about limitations. So we expect it not to work correctly. So I expect you to say, how would the two-way handshake handle this situation? How would it handle this situation? And what would be the problems therein? Just basically to try and show that two-way handshake cannot handle those problems. Then it says, a three-way handshake problem is, however, more suitable for establishing a client-server connection in an unreliable network scenario. Describe the normal operation of a three-way handshake protocol, and you show the sequence numbers. Then lastly, with the help of appropriate diagram, explain how the three-way handshake protocol would handle the following scenarios which can occur in an unreliable network. And I expect to see that the three-way handshake protocol would handle this one better than the way the two-way handshake would have handled this. So I really would want to see how you'd answer those two questions. That you know that the two-way handshake protocol cannot handle, or the problems that will arise when it tries to handle those situations, and that those limitations would be overcome by the three-way handshake. If you can answer this question, that would be good. Just think about it and see if you can answer it. This is the same question, but rephrased in a different way. So just look at it again and see if you can answer it. Of course, there are other questions that follow after that, but this part expects you to know the difference between how a two-way handshake protocol handles certain scenarios when it's in an unreliable network vis-a-vis how the three-way handshake would handle the same thing. Now, these questions are in your classroom. I think it is called revision questions. So there's somewhere where you have revision questions, and these are just some questions from past papers which I picked up and put there. So as we go along, just be checking for similar questions on the topics we have covered and see whether you can answer them. And I think after about 2 more weeks, we will have our first cut, which will include all these things. So I have already looked at your calendar and I've chosen the 3rd of May as the first cut you're going to have. It will be based mostly on this theory we are covering. This theory we are covering will most likely be covered in the first cut. So just be aware that it's on the 3rd. I hope there's no holiday. It's on the 3rd of May. It's a Friday, and it will be a physical cut. It will be done in the lab. So look at those questions, see if they can help you understand better the topics we are covering at the current moment. And if you have any questions, please ask before we finish this topic. So as I've said, next time we will review the question from Ngugi, Jerry, and then we will move on to the next topic, which is how do we terminate a connection? Once you've sent the data, how do we terminate a connection? With the understanding that the internet is unreliable, how are we able to terminate the connection without losing data? Because the TCP must do that for the application. The application must terminate a connection without losing any data that it was trying to send. Okay, so we meet on Friday. I believe by that Friday you should have finished programming the first assignment. And so I'm preparing for you to upload it. Yes, do we have a question? Now, I mentioned that those who have missed class should tell me why they're missing class, because I really don't think they should even do the cut. There are people here who have not been attending class, then they'll suddenly appear on the day of the cut, wanting to do the cut. I think I will stop them. All right, thank you so much. Let's meet on Friday.